Hi, I'm Steve Chien, and I'm going to be speaking about work done with my co-authors Chien and Jagriti Agrawal, and I'm going to be talking about scheduling with complex consumptive resources for Planetary Rover. So the particular problem that I'm going to be talking about is best illustrated by our use case, which is scheduling the energy in waking up and sleeping for the Mars 2020 rover Perseverance. So the rover gains constant energy through radioisotope decay of an MMRTG, but being awake, just being awake, drains more energy than the MMRTG produces. So basically the rover must shut down and sleep in order to gain energy, and so it takes naps in order to have enough energy to do the science activities it wants to do. Depending on the new activity that it wishes to schedule and whether it's close to or within an existing wake period, it may be necessary to extend an existing wake. And varying the duration significantly of these overlap periods makes it very difficult to find good places to schedule new activities, because it has to take into account the energy used, which is dependent on when exactly we place the activity. And the most computational part of the onboard scheduling algorithm for the Mars 2020 rover is in fact generating and placing these wake-ups and shutdowns for the activities. So there's a certain set of activities that are placed on the schedule, and the rover must be awake during certain classes of activities. And the rest of the time it sleeps in order to save energy, and it has to wake up and shut down in between these time periods, which takes time. So there are two not so interesting cases. One is where the new activity is completely encompassed by an existing awake, and so there's no additional waking up energy caused. If the new activity is completely in a sleep period, it's disjoint from the existing wakes. It's a wake period. It's an island of its own. The duration of the awake is fixed because there's no need to extend an existing awake period. Again, the awake energy is constant regardless of where in that interval we place it. So again, those are the easy cases. The hard cases are when it's at the edge of one of our existing awake periods, and the question is how much overlapping this awake period is it? If it's just a little bit, there's only going to be a small amount of savings of energy. If it's a lot, it's going to be almost as much as, a completely encompassed in the awake period. And so it depends exactly on how much overlap there is. And these cases are split into whether or not they lead or trail an existing awake. And that's relevant because the wake up and shutdown time period is not symmetric. Those are not the same. And in fact, in general, they may not be the same. There's also a minimum awake period and minimum asleep period, because you don't want the rover to be waking up and sleeping, frantically all the time, because that's not a very productive thing to do, because while you're waking up or shutting down, you cannot do science activities. So the challenge is to figure out how we handle these cases 3 and 4, where the awake duration depends on the activity start time, and that's the interesting case. And so there are 3 algorithms that we proposed and implemented. The first is max duration. You just assume that you're going to take the full energy hit of the entire new island, even if it overlaps. So this is sound, because it's a conservative estimate on energy. It's simple to implement, but the con is it's over conservative because it can be double counting some energy, and that means your schedule is going to be incomplete when that energy makes a difference. The second approach is probe, which is you just pick a time, and then for that time you try and validate if you have enough energy. And so when you pick a time, you determine which of the cases and the exact timing, and this is in fact the method that ended up being implemented in the Mars 2020 onboard scheduler. The third approach is sort of the most elegant approach, and this is what we call the linear approach. And so you know the case where there's no overlap, you know the case where there's complete overlap, and you linearly interpolate in between there, assuming that the linear consumption, in fact, depending on the amount of overlap, is the appropriate relationship, which in fact for our power model, in fact it is. And so the pro is this is sound and complete, and the con is it's more challenging to implement. There's different calculations depending on exactly where in the interval you are, and the different leading and trailing cases are different because there's different discontinuities, because as we said, the wake up and shutdown are different lengths. So we tested these three approaches on a set of what are called sol types, which are the best guesses as to the kinds of science activities we expect to operate on the Mars 2020 rover. And we vary the incoming state of charge because, in fact, this is an energy test. And so we're trying to understand exactly what is the challenging threshold of energy. And so the first thing that we notice here is that the number of activities scheduled with varying incoming state of charge, which is shown at the bottom, it shows that max awake or max duration is actually strictly underperforming. That's the blue line here. But the linear and probe are very similar, even though the linear is complete and the probe is not. Why is that? Well, it turns out that when we run it over the whole scheduler, generating the whole schedule, that's actually a whole bunch of iterations of scheduling all the activities one to n. And so it's very hard to see the differentiation there. So instead what we do is we generate a bunch of partial schedules. We schedule up to I activities, and then we present that problem of scheduling now in that context, presenting the problem of scheduling the I plus first activity. Now we calculate how often you're able to place the I plus first activity from the same schedule of 1 to I activities. And as we can see here, now it's much more clear that max awake or max duration performs the worst in terms of completeness. And there's a very, very slight outperformance of linear over probe, but it's very slight. Why is that? Well, it turns out the wake-ups and shutdowns are only 5 and 10 minutes long. So the amounts of overlaps, the case 3 and 4, are actually, of the straddling and partially covering at the start or the end of the awake or asleep place are not very common. And so what we did is we did a synthetic case where we increased the duration of the wake-ups and shutdowns to 30 and 60 minutes. And then, as you can see here on the right here, you can really now see the difference. So if the wake-ups and shutdowns or these overlap periods are larger, then it makes a bigger difference. And finally, we show the runtime analysis. The runtime of these different algorithms, it's not actually a surprise that the probe actually is the fastest and that the linear takes more time. And interestingly enough, the max awake actually takes the longest amount of time. And that's actually because when it fails to place and schedule an activity, it actually has to iterate more and keep trying and place the activity, whereas the other approaches just immediately find the schedule. And these differences in runtime are actually significant because a scheduler run could take quite a bit of time, up to 1 minute, because the onboard computing resources are not great. So future works, this analysis didn't really take into account the preheats and maintenance heating, and what that means is that there are setup activities for each activity, and so those setup activities are additional energy cost, and also depending on where you place the activities, you might be able to share the setup activities. And then finally, we'd like to do more analysis of the runtime with actually a flight-like processor. These benchmarks were all done with a workstation. Finally, to summarize, we just like to summarize and say that generating and scheduling activities with these complex consumptive resources is quite challenging when depending on the placement, your resource consumption is different, which is the case that we have. We showed algorithms for a specific sub-problem, a specific type of problem in that, which is energy scheduling for the Mars 2020 rover. We showed a sound and complete algorithm, we showed a heuristic algorithm, and we showed a conservative algorithm. And we showed that in the practical use case that we were concerned in for Mars 2020, the heuristic algorithm was close enough to the complete algorithm, the complete and sound algorithm, linear algorithm, and that's what in fact they implemented for the Mars 2020 rover. Thank you very much.